welcome to the deep dive. Today we're jumping into a topic that, well, might sound a bit technical on the surface, but honestly, it's absolutely critical if you're working with data. We're talking about Databricks Delta Schema issues. Think about your data pipelines, right? They need to run smoothly. And schema problems. They're often that hidden snag that can just grind everything to a halt. So for this deep dive, we've got this fantastic resource. It's called Databricks Delta Schema Issues Comparison Table with Mitigations.pdf. And really, it's a goldmine. It gives a super clear breakdown of the common schema challenges you might hit in Delta Lake. And even better, it tells you exactly how to fix them.
Yeah, absolutely. And our goal today really is to give you that practical knowledge, those moments where you go, okay, I get it now. We want to turn those potential data headaches, into challenges you can actually manage. Because understanding these issues and critically knowing the solutions, that can save you so much time, so much effort in your pipelines. It's huge.
Okay, then let's unpack this. We're going to dig into the specific kinds of schema issues that pop up, and then we'll look at the powerful ways to mitigate them based on this document. Now, Delta Lake's big strength is its ACD properties, right? Atomicity, consistency, isolation, durability, and it enforces schema. But even with all that, schema issues can still happen. And just for context, we'll probably talk about those common data layers. Bronze for the raw stuff, silver for clean data, gold for the final aggregated results. We'll see where these problems tend to show up.
Exactly. That context is key. #tag1, schema drift, unexpected changes.
All right, first up, schema drift. So imagine your incoming data just changes on you. Suddenly there's a new column you didn't expect. Or maybe one's missing or it got renamed. No warning. Just bam.
Yeah. The unexpected guest, as you said. And typically this happens during ingestion, right? Especially if you're using things like autoloader or reading streaming data. It hits that bronze layer first, usually. That's where the raw, sometimes unpredictable data lands.
Okay, so the curveball arrives. How do you catch it? What does the source say?
Well, there are two main immediate tactics. First, you can use an option called mergeSchema true when you read the data.
Oh, so that's like telling Spark, hey, if they're new columns, just accept them. Kind of autopilot for the schema.
Precisely. It lets the schema evolve automatically as new columns appear in the source. It merges the schemas. Or the alternative strategy is maybe a bit more cautious. You just store the raw incoming data as, say, JSON text or plain text first in bronze.
Okay, so you capture everything as is.
Right, and then you deal with parsing it out, applying a schema later, maybe in the silver layer where you have more control.
So delaying the schema definition.
Exactly. The key idea for drift is expect change. Build pipelines, assuming the source will change, and use options like mergeSchema or this delayed parsing to handle it. #tag2. Schema evolution, manage changes.
Okay, that leads nicely into the next point. Schema evolution. How is this different from drift?
It's a great distinction to make. Drift is unexpected. Evolution is more intentional. It's the automatic but still managed incorporation of schema changes into your Delta table.
So it's not random chaos, it's planned adaptation.
Exactly. It happens during write operations, specifically when you're writing to a Delta table. And again, that mergeSchema option is the key enabler here.
Right.
This often affects bronze and silver layers, letting your tables adapt as requirements change, but in a controlled way.
So the strategy is, well, pretty straightforward. Enable mergeSchema when you write, like when appending to bronze. But the document also really stresses checking the schema history, using describe history. Why is that so important?
Oh, describe history is incredibly powerful. It's like a time machine for your table's metadata. It gives you a complete audit trail. Every schema change, every data change, who did it, when.
Wow, okay.
So if new columns are appearing via mergeSchema, the history tells you exactly when and how. It's essential for tracking, for debugging, for governance, really.
So mergeSchema is the tool, history is the logbook.
You got it. Keep an eye on that history. #tag3, data type conflicts.
Okay, so drift and evolution handle new columns. But what if the type of data in a column is wrong? That brings us to data type conflicts. Pretty self-explanatory, right? Incoming data just doesn't match the type defined in your table's schema. You expect an integer, you get a string, that kind of thing.
Absolutely, the classic string for a number problem. Or sometimes it's more subtle, like you expect a precise decimal, but you get a float, which can wreck your calculations downstream if you're not careful.
Yeah.
This pops up a lot during ingestion, during appends. Again, bronze and silver layers are the hot spots.
The document suggests casting fields explicitly. before you write.
Yes, that's often the most robust approach. Be explicit. If you know that ID column might sometimes look like a number but should always be treated as a string, you use Sparks functions like coltity.cast string. You force it.
Take control.
Exactly. Or, similar to the drift mitigation, you could store raw text in bronze.
Right, and then do the careful parsing and casting in silver.
Yep. It delays the problem but gives you a dedicated place to handle it cleanly.
So the golden rule seems to be, define types clearly and cast early if you can.
Pretty much. Establish those data contracts between layers. Don't let Spark guess too much if you can avoid it. Cast explicitly. #tag for nullability mismatches.
All right, next up, nullability mismatches. This is about whether a column is allowed to have null values or not, right?
Exactly. And it's often a sneaky one. Your table might have a not NOL constraint on a column.
Like a user red, maybe? Can't be null.
Right, but then suddenly the source system starts sending nulls for that user id.
And boom, pipeline breaks. Constraint violation.
Yep. Seen it happen many times. It often bites you during override operations or just when schema enforcement kicks in. And it tends to affect silver and gold layers more because that's where you usually enforce stricter data quality rules.
Okay, so how do we fix it? The source mentions alter table.
Correct. If you decide that, okay, this user id can actually be null now, you can use SQL to modify the table definition. Something like alter table, your silver bait of alter column, user id drop, not null.
You explicitly relax the constraint.
Exactly. But the other key point is standardizing how you handle nulls in your ETL process.
How critical is that standardization piece?
Oh, it's vital. You need a consistent strategy. If a source might send nulls, decide up front. Will you allow them in the table? Will you replace them with a default value? Will you filter those records out? You need a plan. Don't just let nulls cause random failures.
Right. So define the schema and the null handling rules.
Precisely. Use alter table carefully, but think about the whole null lifecycle. #tag 5. Column reordering.
Okay, moving from column properties like type and nullability, what about their order? That brings us to column reordering.
Yes. This happens when the sequence of columns in your incoming data changes unexpectedly.
And this only matters if your code relies on position. Right. Like if you assume the third column is always the user ID.
Exactly. If you're reading data and just assuming column 2 is the user ID, and then suddenly it becomes column 4, your logic breaks.
Where does this usually happen?
The source points to batch ingestion, especially if you're using schema inference. The system might read files in a different order, infer columns differently.
And shuffle the deck, so to speak.
Pretty much. It's mainly a bronze layer issue right at that initial load.
And the advice is crystal clear here.
Yeah.
Define explicit schemas. Don't rely on inference.
Absolutely. Create that struct type blueprint for your data. Spell out every column name and type.
So you're locking in the names and types regardless of physical order.
Exactly. And the second part of the advice, always map columns by name, not by position in your code.
Makes sense. Use the name, trust the name.
That's the golden rule. Explicit schema, name-based mapping. Avoid positional dependency like the plague. #tag 6, nested field changes.
Okay, let's get a bit more complex.
Yeah.
Nested field changes. This is about changes inside complex data types like JSON columns or structs, right? A field appears or disappears within the nested structure.
Yeah, exactly. You might have a JSON column called event details, and suddenly a new field location appears inside that JSON. Or maybe an existing nested field changes its type. This is super common when you're dealing with semi-structured data sources, APIs, event streams, that kind of thing.
Right, lots of JSON.
And it impacts bronze and silver layers, typically. Bronze captures the raw structure. Silver is where you often parse it out.
So the recommendation is, again, store the raw JSON in bronze.
Yes, that seems to be a recurring theme for handling unpredictable structure. Capture the raw string first.
And then in the silver layer, parse it using an explicit schema. How does that help with nested changes?
Well, when you parse in silver using Sparks from JSON function, you provide a schema for that JSON. That schema defines what you expect to find inside. If new fields appear that aren't in your schema, they're typically ignored by default or handled gracefully depending on options.
So you control the parsing. You decide which nested fields to bring into columns.
Exactly. You apply structure explicitly at the point of parsing. It gives you that control over how nested evolution is handled.
So delay parsing complex types. Use explicit schemas for the parsing step.
That's the pro tip for nested data, definitely. #tag 7. Column dropping.
All right, we've covered new columns, changed columns, reordered columns. What if columns just vanish? Column dropping.
Simple, but painful. A column you expect that your downstream code relies on just isn't there in the incoming data anymore.
Leads to nulls where you didn't expect them, or maybe just outright pipeline failures.
Yep. If your code tries to select call, important metric, and it doesn't exist, boom. Happens during ingestion, affects bronze and silver. If it's missing early, it's going to cause problems later.
Okay. Mitigations. The source suggests filling missing fields.
Right. You can use functions like coalesce. So if a event type is missing, maybe you fill it with a default string like unknown.
Coalesce, event type,
Yeah.
lit, unknown, something like that.
Exactly. Provides a default value, prevents immediate null issues downstream.
But the source also mentions setting up alerts, like actually checking if expected columns are present.
Yes, and this is often overlooked, I think. Filling defaults is good first aid, but knowing the column is missing at all is better. You can write simple checks, like the Python example in the doc comparing expected column sets to actual data frame columns.
Expected usered event type versus set df.columns.
Right. If there's a difference, log it, send an alert, catch the problem proactively.
So validate your schema expectations actively. Don't just react to nulls.
That's the key. Monitor for those gaps. #8, column renaming.
Okay, number 8, column renaming. This feels similar to dropping, but instead of disappearing, the column just has a new name. Maybe user becomes customer identifier.
Exactly. Someone upstream, maybe in the source database or an earlier ETL step, renamed a column. Didn't tell you.
And all your code referencing the old name breaks.
Pretty much. Hits you during ingestion or in transformation steps. Bronze and silver layers again. Often a sign of, let's say, communication gaps between teams or systems.
So how do you handle this? The doc mentions mapping tables or explicitly renaming.
Yeah, two main approaches. You could maintain a separate mapping table or configuration file that says old name maps to new name. Your ETL code reads this map and applies the renames dynamically.
More flexible for many changes, maybe.
Potentially, yeah, especially if renames are frequent or managed centrally. The simpler alternative for fewer changes is just to use Spark's built-in function with column renamed.
So df dot with column renamed. Old name, new name. Hard code the fix.
Right. Quick and direct for specific cases.
So the takeaway is to have some mechanism, whether it's code or config, to handle those renames gracefully.
Absolutely. Build in that resilience to upstream naming changes. #9. Schema inference variability.
Okay, this next one sounds like an issue caused by the tool itself. Schema inference variability.
It can be, yeah. Schema inference is convenient for exploring data, right? You point Spark or autoloader at some files, say infer schema true, and it tries to guess the data types.
Sounds handy, but risky.
It can be very risky in production. The problem is, it might guess differently based on the data it sees in different files or different batches. Maybe the first 10 files have an id column that looks like number, so it infers integer, but the 11th file has an ID like ABC123.
So now it might infer string. And you get inconsistent types across your dataset load.
Exactly. It leads to these subtle, hard-to-track-down inconsistencies, primarily a bronze layer issue, right where that inference happens.
So the advice here seems pretty forceful in the document.
It is, and for good reason. The advice is, don't rely on schema inference in production, period.
Always define explicit schemas. Use that struct type.
Yes. Spell out exactly what you expect each column's name and type to be. Provide that schema when you read the data.
Takes away all the guesswork.
Completely. It's the ultimate safeguard against inference surprises. Inference is for quick dev checks, maybe, not for reliable pipeline.
Explicit schemas, non-negotiable for production. Got it. #10. Backward incompatible changes.
Okay, last one. Number 10. Backward incompatible changes. These sound serious. They are the big ones, yeah. These are schema changes that Delta Lake cannot automatically merge or handle smoothly. Think dropping a column that downstream processes absolutely rely on, or changing a column's type in a way that breaks existing logic, like changing a string to a number when people were doing string operations on it.
So these require manual intervention. You can't just rely on mergeSchema.
Definitely not. These typically arise from deliberate table evolution actions: alter table, drop column, alter table, change column type in a non-compatible way. And they have the biggest potential impact on silver and gold layers, where stability is crucial for consumers like dashboards or ML models.
I can imagine. Breaking the gold table schema could take down a lot of things.
Oh, absolutely. This is where things can get really painful if not managed carefully. But it's also where Delta Lake offers some unique lifesavers.
Right. The document highlights two key things here. First, Delta Lake time travel.
Yes. This is huge because Delta versions every change. If you make a backward incompatible change that breaks things, you can literally query or restore the table to the version before the change happened.
Like an undo button for your entire queue.
Exactly like an undo button. Using option version ASOF, you can roll back time. It's an incredible safety net.
Wow. Okay, that's powerful. And the second point, careful planning.
Crucial. Time travel is the cure, but prevention is better. Before making any potentially breaking change like dropping or retyping a column, you need rigorous planning. Understand the downstream impact. Validate the change. Maybe test it on a cloned table.
And describe history again, probably, to understand the current state.
Absolutely. Check the history, know what you're changing, careful planning, communication, validation, and having time travel in your back pocket, just in case.
So plan meticulously, execute carefully, and know you have that Delta time travel safety net.
That's the strategy for the big, scary changes. Looking back at all 10 of these, it really paints a picture. Schema issues will happen when you're dealing with real-world evolving data. It's almost inevitable. But the good news is, with the features in Databricks Delta and the strategies we've talked about, things like mergeSchema, explicit schemas, history, time travel, they are absolutely manageable.
It's not about avoiding change. It's about being prepared for it.
Exactly. It's about building resilient pipelines that can adapt or at least alert you when things shift rather than just falling over. It's proactive versus reactive.
So wrapping this up, what does this all mean for you listening right now? Well, hopefully this deep dive has armed you with some really practical insights. We've taken this potentially overwhelming topic of schema management and broken it down into clear steps. You now have a better idea of what can go wrong and, more importantly, what you can actually do about it. You're better equipped for those real-world data challenges. So here's a final thought to leave you with, building on that last point about backward compatibility and time travel. Considering that power, that ability to rewind, what historical data problem, maybe some schema mess up from your own past projects, would you go back and fix right now if you had Delta time travel back then? Something to think about how these tools could have changed things and how you can apply them going forward.